My name is Lily Wilner, and I'll be doing the freezing point depression lab. You will see that regular water will freeze in a home freezer, but salt water has a much lower freezing point and will not freeze at a home freezer. Step 1. We will add 1 cup of water to each of our 2 water bottles. We also add it to the other water bottle. Make sure that you label each water bottle as either water or salt solution. It's very important not to get these two mixed up. Next, we will screw the cap onto the water bottle that says water, and we will set it aside. Then take the salt, or the other water bottle that says salt on it, and add some salt to it. Add a teaspoon of salt about, and put it in, and dip. Make sure it all gets in there. Then what you do is you screw the cap on, make sure it's really tight, and then you just shake it up. You want to make sure that all the salt is dissolved. You just keep adding salt. If there isn't any salt at the bottom, you just keep adding more salt until when you shake it, there is salt left at the bottom. Oops. Oh, there's definitely salt at the bottom. There's definitely some salt at the bottom. I don't know if you can see it, but you should definitely take my word for it. There is salt at the top. So, the next step, we take both the salt solution, which is just salt water, and the water solution. And you next make sure you have room in the freezer. And then you take both of them to your freezer. We're going to lie them down. Done! It's been 3 days since we did the experiment, and as you can see, the plain water solution has completely frozen solid while in the freezer, and the salt solution has not. It is still in liquid form. When a substance freezes, its particles take on a specific pattern. But when you add a solute to water, like we did in our experiment, it disrupts the pattern. As a result, more kinetic energy must be taken from a solution than from a pure solvent to make the solution freeze. This makes the freezing point of a solution lower than that of a pure solvent. The difference between the 2 freezing points is the freezing point depression. A real-life example of freezing point depression is when we made ice cream in class. We mixed salt with ice in order to give the ice a lower freezing point. This made the ice colder, which made the ice cream ingredients cold enough to create ice cream.
Hi, I'm Troy Davies, and I'll be doing the boiling point elevation lab. First, we'll be taking the same amount of water and vinegar and putting them on the stove and waiting for them to both boil. You'll find that the vinegar will boil at a higher temperature than the water will. First of all, we'll take about 1 cup of water and pour it in a pot. We'll also measure out the same amount of vinegar and pour it into the other one. Now we'll take them both to the stove and heat them up. This is the vinegar and this is the water. As you can now see, the water is boiling at 100 degrees Celsius. The vinegar has finally started to boil. The vinegar is now boiling at around 102 degrees. Boiling point elevation refers to the fact that solutions boil at a higher temperature than pure solvents do. We proved this to be true when we found that the boiling point of vinegar, which was at 102 degrees Celsius, was higher than the boiling point of water at 100 degrees Celsius. This makes sense because vinegar is a solution with a solvent, while water is a pure substance. Because boiling point elevation is a colligative property, it depends on the concentration of particles, not their identity. In terms of particles, it takes additional kinetic energy for the solvent particles to overcome the attractive forces that keep them in the liquid. Therefore, the presence of a solute will raise the boiling point of the solvent. So the more solute there is, the higher the boiling point will be. For example, a solute, such as antifreeze, when added to a solvent, such as radiator water, will lower the freezing point of the solution in the radiator so that it won't freeze so quickly.
Hi, my name is Julia, and I'll be doing the vapor pressure lowering lab. In this lab, we will put rubbing alcohol, 20 milliliters, in each cylinder, and in one of the cylinders, we will crush up 3 tablets of aspirin. In the end, we will see that the pure rubbing alcohol will evaporate quicker than the one with 3 aspirin tablets. First, I will put 20 milliliters of rubbing alcohol in each one. First, I will pour 20 milliliters of rubbing alcohol in each cylinder. Then I will pour another 20 milliliters in the second cylinder. After I have 20 milliliters of rubbing alcohol in each, I will crush up the 3 aspirins on this piece of paper. After the 3 tablets are crushed, we will pour them into the cylinder marked with an A. After, we will shake it. It's gross. It's gross. Next, we will place the 2 cylinders in a similar environment and check back on them in a couple of days. As you can see, the pure substance of rubbing alcohol evaporated more than alcohol mixed with aspirin. For instance, when people have high fevers, they may rub themselves with pure alcohol because it evaporates quicker than some substances and helps the fever go down. In our experiment, we noticed that pure alcohol evaporated quicker than alcohol mixed with a solute. This happens because a solution that contains a solute that is not easily vaporized always has a lower vapor pressure than a pure solvent. Pure solvents have a higher vapor pressure, which means it has more molecular forces, which releases more particles into the air.